Right. Okay, let's get started. Welcome to the next season of our seminar series on numerical linear algebra. My name is Stefan Güttel, and it's great to see so many familiar names on the call. So on behalf of the organizing committee, we would like to welcome you back after what we hope was an enjoyable summer break. Now, for those who are new to the seminar, if you would like to ask questions during the talk, you're very welcome to do so by using the Zoom chat. I will then either read out the question to the speaker and audience or invite you to repeat the question using your microphone. But we first need to give permission in order for you to be unmuted. Now, it's a real pleasure to introduce today's speaker, Karl Meerbergen. Karl is a professor at the Department of Computer Science at KU Leuven, and he is very well known to many of us. Karl has a wide range of interests and many important research contributions, including eigenvalue problems, preconditioning, and parallel computing. And maybe I can highlight in particular his SciEM review paper on the quadratic eigenvalue problem, co-authored with friend Tisseur, which has been and still is an invaluable resource for many of us. Today, Karl will tell us about rational approximation and linearization of finite element models with nonlinear frequency dependencies. So Karl, whenever you're ready.
I'm ready. Thank you very much, Stefan. And thank you, the organizers, for inviting me to this exciting series. Today, I'm going to talk about the collaboration with engineering colleagues of mine. And it is based on rational approximation and linearization, which is a topic I've been working on the last 10 years quite intensively. The idea is the following. We want to analyze vibrations, and the classical analysis consists of a frequency domain analysis or a Fourier domain analysis, where finite element discretizations or boundary element discretizations are used. And typically finite element discretizations lead to sparse linear systems of the form that are shown here, where the frequency omega appears in a linear or a quadratic form. And the frequency analysis, which is also called frequency sweeping, then consists of computing x as a function of omega, which is basically solving a large number of linear systems. I'm not going to talk about that topic today. I'm going to talk about a related topic, which is time stepping. Now, time stepping is not used classically in these for this type of analysis, and that's the topic of today. Of course, we can also do eigenvalue computations. Eigenvalue computations are very popular in the study of vibrations, but surprisingly, I'm not going to talk about eigenvalue computations. All right, so the motivation lies in the following observations. There are two trends in mechanical engineering. One is the appearance of nonlinear frequency dependencies, as they also show up in nonlinear eigenvalue problems. Typically, they are the result of new materials, damping materials that are used in all kinds of devices. But more importantly, perhaps, is the use of time domain models. Typically, in mechatronic systems where you have moving parts, these problems are nonlinear in time, and you can only do that properly in the time. Now, in the context of digital twins, which is an important topic for our community, you want to do time integration very fast. You want to update parameters of the model based on measurements that come in. And basically, you want to have a digital model of a physical asset that follows or predicts the behavior of the asset over time. And usually you have a coupled system that consists of several components, and such a component could be described by the equations that we will look at today. So that's a general motivation of what I'm going to present. Now, let's go back for a short time to second order systems. This here is a second order differential equation, or a system of second order differential equations, where MC and K, there should be a K here, are matrices, usually sparse matrices, and X is a state vector that depends on time, and we have a first and second derivative here. Well, we all know that we can write this as a first order system by what we call a linearization. And what you see here is that by multiplying out the first row of the equation, you get this equation back, where the second row imposes a structure on the state vector as a function of time. So we see, for example, here that the first component, the derivative of the first component is equal to the second component here. Now, In general, we have a concept called linearization, and it is used for solving the quadratic eigenvalue problem, for example, where you again have a linear system. In this case, where you have this linear system as a function of S, which is then written into a linear system using a pencil. So S here appears in a quadratic way, and in this linearization, it appears in a linear way. And notice that the solution vector has a very special structure. The solution of the system appears twice. You have the first component, which is x, and the second component, which is sx. And this sx is obtained again by looking at a second equation that imposes the structure of this vector. And the fact that we have a linear system in S allows us to do time stepping by solving a related differential equation, fast frequency sweeping, and eigenvalue computations. And I'm going to talk about time stepping, but of course the two other topics are also related to this talk. Now, in general, when we have a polynomial matrix P, where P is a matrix whose coefficients are polynomials in some degree, we can always write what we call a linearization, which is a linear pencil. And we talk about the strong linearization when there is a one-to-one correspondence between the eigenvalues of the polynomial matrix, which is defined by the values that make the determinant, the values of S that make the determinant 0, and the eigenvalues of the matrix pencil. And this allows us to compute eigenvalues, for example. And in the case, again, the case of a second degree system, this is a possible linearization. And you see that indeed S appears in a linear way. This is a linear pencil. And this is also a strong linearization in this case. Now, in many problems, this is an example of a plate model with poroelastic damping. We have a stiffness matrix here, a mass matrix, SQH, which is typical for the acceleration term with a mass matrix. And here we have a term which corresponds to a damping term in the matrix. And we have here a rational function of S. In this case, the engineers have written the damping term themselves in a rational term, but this is not always the case, as we will see further. And this can be linearized as well. It can also be written as a linear pencil, a system with a linear pencil where S appears in a linear way. And so again, you can solve this system by solving a system of a much larger dimension because of the linearization. So it depends on the value of P. If P is 10, for example, then you have a system which is 10 times the size of the original one. But in many algorithms, we can exploit the structure of this type of linear systems, but I'm not going to talk about that. Now, again, here we can introduce a concept of strong linearization, but I'm not going to do that because usually linearizations of rational matrices are matrices with coefficients that are rational functions. We can also write a linearization, so a pencil that produces the same eigenvalues as the rational matrix, but we have to be careful. Most linearizations have eigenvalues that are also poles of the rational matrix. Not always, it depends on the situation. So in this example here, for example, we have a linear term, and then we have this rational term. Here we have a linearization. This linearization has the same eigenvalues as R, but if A1 is a singular matrix, then S equals 0, which is a pole of R, is also an eigenvalue. So it depends on the situation whether we have a strong linearization or not. In our examples, we usually have a matrix A1, which is not of full rank, which means that the poles are in general also eigenvalues. It can be avoided by determining the rank of A1, doing a decomposition, and then reduce the dimension of L, but this is not always easy to do in practice. So we usually, well, we do not always do that, this rank detection. And I will tell you what the consequences of that are in the context of this talk. Here is a nonlinear problem, nonlinear inner frequency that I will use in the examples. It's a clamped sandwich beam, so it consists of two steel plates, and in between the two plates is a damping material. And if you do the final element analysis of this system, you again have a stiffness matrix and a mass matrix, and a damping term which comes from this damping material in between the two steel plates. And in this case, it looks like this. The numbers that you see here are determined for measurements, so it's not a formula that is devised from some theory. So these are really found by matching experiments with this type of model from which these 4 parameters are determined. And what we want to do is time integration with such a model. Okay, now in order to do time integration, we want to design a system that is linear in S. And how do we do that? Well, there are different approaches. There are 2, in my opinion, that we could use. The simplest one is to use sampling methods, which are, for example, based on Leuven matrices, where you only have to evaluate y as a function of S. So we have to determine some output, which is a linear combination of the state vector. And then we're going to sample y. And this is very simple because what you have to do is solve a linear system with A. It doesn't matter what A is, it's matrix as a function of S. You don't have to use the structure of this matrix, you just have to solve linear systems. So it's a very appealing type of techniques because they are relatively simple to use. The only downside is that the computational cost for building such linearization can be quite high. And for that reason, my engineering colleagues wanted to look for other techniques. And the other class of techniques are related to work that several among us have been involved with the last 10 years. And this is based on rational approximation and linearization. So what we do is approximating A as a function of S by a rational polynomial or rational matrix. And then we write down the linearization and use that linearization in time integration. It has the advantage of linear models. The size may be quite large. I'm not going to talk about that here. The only condition is that we can easily provide a rational approximation. And that's not always possible, not always easy, but in many situations we can do that. So the approach that we use is the following one. We are going to assume that we can write the matrix in this way. Note that I don't have a term of degree 2 here, just to make the talk a little easier to write down on slides. So there should be a second order term as well, but let's forget about that at the moment. Important is we have a linear part in S, and then we have a linear combination of matrices multiplied by scalar functions. And this we call the holomorphic decomposition because we assume that the functions gi are holomorphic on the imaginary axis. In our case, the imaginary axis is important because the state vector on the imaginary axis determines the dynamics of the system. And we also assume that the GIs are real functions, well, or extensions of real functions. What I mean by that is that if you apply the function to the complex conjugate of Z, we obtain the complex conjugate of the function of Z. And again, we are going to do 2 steps. We are going to approximate the nonlinear functions by rational functions. So the GIs are approximated by RIs of some degree. And this is then written, then the linear system with R, with a rational matrix, is written as a linearization. In this particular case, we want a linearization that leads to that has a real pencil and that is stable. And these 2 conditions are quite important for doing time integration. Okay, now I'm not going to explain all the details of rational approximation. I will say a few words later about the AAA method, which is the last one that has been introduced in the long series of contributions to using rational approximations for eigenvalue problems. I think it all started with a paper by Jiajun Bai and Yangfang Su on using Padé approximations. Then we had the spectral discretization, which is a very useful tool for the delay differential equation. We had analyses, which is based on potential theory, which was an idea by Stefan Güttel. And then we have AAA, which arose from several discussions with a number of people present in this audience. Okay, I'm going to explain a few words about the AAA method. What we have is the following. We have a function g, which we want to approximate by a rational function, and this rational function is going to be written in barocentric form. It consists of the ratio of 2 rational functions. In the numerator, we have a function n, in the denominator, a function d. And the only difference lies in the fact that we here add the function value of g in a support point. So the z the z's are the support points, xi are the weights. So it looks a bit like a Lagrange formulation. It's called the barycentric rational form. And the AAA method is a method that builds such a approximation in an iterative way using a greedy procedure. And this was proposed by a number of people in quite recently, a few years ago. Now, how does it work? Well, it's a method that selects support points from sample points. So you have to discretize the domain in which you want to approximate a function by choosing a number of points. And what you're going to do is select a support point from this point by looking at the approximation error that we have so far. So it's an iterative procedure that adds a new support point at each iteration. So the new support point is added by picking the point with the largest error. And once that is done, the weights are computed by minimizing what we call the linearized residual. Is the residual that we obtain by multiplying the function by the denominator, by this rational function. And by doing that, we find a least squares problem, which corresponds to finding the smallest singular vector of a Leuven matrix. And this Leuven matrix is written here. So Leuven matrix has coefficients that correspond to divided differences between the sample points and the support points. Okay, so that's the method, the AAA method explained briefly. Now, in our case, what we are going to do is approximate the functions on the imaginary axis. And because we want to keep the symmetry with respect to the functions that we have, so we assume that the functions satisfy this property here, we're going to choose points in the upper part of the imaginary axis and then reflect these points along the real axis to obtain the blue point. So we're always going to add two complex conjugate points in one iteration. And by doing that, we can ensure that the weights are complex conjugate and that we can obtain a real function. So the rational function that we obtain also behaves like a real function with the same property as here. And that's what we need for making a real linearization later. Okay, now the Leuven matrix that we obtain has a special structure. It looks like this. We have on each row corresponds to a support point. And the next row then corresponds to the complex conjugate of the support point, the sample point. And the columns correspond to support points. We have the column for support points Zj, for example, and the next column to the complex conjugate. And because of this structure, we can obtain weights that are also complex conjugates. And so we exploit this structure to find weights with that particular structure. Okay. So now I have to explain how we come to linearization. This is a bit technical, perhaps. In general, we're going to write the rational functions in this form. It's not always possible to do that, but assume that we have a rational function which is written in this way. So we have a vector A and a vector C here, and in between the inverse of a pencil. And this function can be can be seen as the Schur complement of this matrix computed for the first element, the 1, 1 element of this matrix. Now we can define this part here. Oops. This part of the rational function as a set of basis functions. We define them here. And then we can consider the A vector as the coefficients that provide the linear combination of the basis functions, and the inner product of the coefficient vector and the basis then leads to the rational function. And it is this basis that we can use in a linearization. So assume that we want to write a linearization for this linear system here. So we have a linear part and here a part with the rational function. What we do is the following. We first write down the equation on the first row, where we have in the solution of the linear system a vector x, and the second part corresponds to a product of the canonical product of the basis functions and the vector x. So the multiplication of this term in the matrix with that part of the solution vector leads to A1R times x. So if you work out the canonical products, A transpose times phi is a scalar. So the canonical product disappears and you have A transpose phi times A1 times x, and that is what we have here in this part of the system. And then the blue part of the system here imposes the special structure that we have on the solution vector. So it imposes that the second part takes that form. So this is the general form of linearization that we always have. Now the question is now, how do we choose C, A, E, and F so that we can plug in a barycentric form? Well, a few years ago, we have proposed such a linearization. It looks like this. So the A vector is this, the C vector is that, and then the matrix A minus SF is here. And you see that the only information in this matrix are the weights xi and the support points z. Okay. In general, we have more than one nonlinear function in an expression like here. And we have to make several rational approximations. For each g, we have to make separate rational approximations. And there are several ways to do that using the AAA method. I'm not going to explain the details for that. There are a number of papers here, but yeah, that could be a talk by itself. And there was a talk by François Tisseur about that some time ago on how you can do in a reliable way a rational approximation of a nonlinear matrix. Okay, now we want to have a real linearization, so linearization with a real pencil, and we can obtain that by exploiting the fact that the support points come in complex conjugate pairs as well as the weights. So here we have an example with 4 points, 2 pairs of complex conjugate points, and by doing a transformation, we can obtain a pencil with real coefficients, and that's what we need for time integration. And this matrix has the same Schur complement, so we have the same rational function. Now, another problem, which is perhaps more important, is the fact that the linearization that we have has an infinite eigenvalue. And for time integration, this is something to worry about. Well, not always. It can be an issue, but in this case, we can easily remove this infinite eigenvalue. So without doing that, we have a differential algebraic equation, and we may have to be careful. And indeed, we have noticed that in the numerical experiments, that sometimes you get instabilities because of that. Now we can remove the infinite eigenvalue from this linearization, and I'm not going to show you how you do that, but when you do that, you reduce the order of the linearization by 1, and you find this linearization here. So this one has the same Schur complement as before. It's just reduced in size, and the advantage is no infinite eigenvalue. Okay, so I think we're ready now to continue with the rest of the talk. Perhaps there are questions. I see in the chat. Are there questions?
I think there are currently no questions, Karl.
Okay, so then I can continue. Okay, so everybody fell asleep, or it was a very clear talk. That was a joke, of course. So what we are doing is making a linearization of this rational matrix. So we have the linear term and then a linear combination of rational functions. And this we can write using a linearization. Now, the eigenvalues of this linearization, there can be two sets. It can be either an eigenvalue of the matrix of the rational matrix, which is good, of course, but it's also possible that the poles of the rational matrix are eigenvalues of L, and the poles are eigenvalues of this pencil here, E minus SF. And this happens when this linear combination of matrices here does not have full rank. In that case, we do have eigenvalues of this pencil as eigenvalues of L. Now, if you want to use L for time integration, the eigenvalues must be stable, otherwise we cannot do the integration. So that means that we have to imply that the poles of the rational approximations of these functions, of the nonlinear functions, have to be in the left half plane. And in this example, or in this application, this is usually the case because these nonlinear functions arise from damping terms. And damping terms, by definition, they are damping to a system. And we indeed notice that the eigenvalues are in the left half plane. So that is very useful. Okay. of what we can do with AAA. It's not a problem coming from engineering, it's a problem from physics. It's a problem where we have 81 functions to approximate by the AAA method, functions of this form. You have an exponential and then a square root. And these alphas here are branch points of these functions. And AAA, surprisingly, well, maybe it's not a surprise, but nicely, is able to approximate these functions in interval in between two branch points. And even more nice is that the poles of the irrational approximation, which are plotted in red here, lie in some kind of branch cut of these branch points of these singularities, and this is also very nice. So AAA is really very good at detecting singularities of functions, and this is something that we can use without using any information about the functions. Okay, now we want to do time integration using linearizations. There is one type of problem for which this is very well understood, and that is a time delay equation, which is here. So here we have derivative, we have a times x, and here we have a delay term, and tau is a delay. So we use the vector x for time in the past. And in the Laplace domain, this equation becomes this one here, where the delay term leads to an exponential in the Laplace variable s. And this is a nonlinear term in s, and yeah, that's what it is all about. Now, for this type of problem, we can also write down a linearization. You can do that using an operator setting, then you find an infinite dimensional linear problem, differential equation. But the initial solution cannot be anything. You have to choose it very carefully in order to have a connection with the time delay equation. Secondly, you have to use the solution from the past. So at time equals 0, you have to know what the solution is in the past. Otherwise, you cannot set a proper initial value. And that's also going to be the case for the applications that we have. So in general, we have this algebraic equation with rational functions in S. We have a linearization that corresponds perfectly well in the Laplace domain with this equation here, where the solution of the state vector of the linear system has a special form involving rational functions. Now the question is, how can we connect that to the time domain using a Laplace transform? So how can we choose the initial values of such an equation to ensure that we have the connection with this equation here? And that's very important. We're going to assume that in the right-hand side, we have an excitation, which is always of this form. So the first component is b of t, and the other components are 0. And I'm going to look at two specific situations, a harmonic solution and an initial value 0. If we have a purely harmonic solution of the following form with this right-hand side, we can make the connection using the Fourier transform with this equation here. So if you have a purely harmonic solution for some frequency f, so omega is 2 pi times f, the frequency, then this equation here gives us the amplitude of the solution. It's a complex amplitude, and in this case we have a clear connection between this linear problem and the algebraic problem here. The second is a problem with 0 initial values. In this case, we can also make a relationship by using the Laplace transform. And again, we have a connection between the first component of the solution of this system of ODEs and this algebraic equation. So the amplitude, if you like, in the Laplace domain is also computed in this way. Now, in general, the situation is a bit more complex if you have some excitation of this form and you have some starting value. So x here corresponds to the original problem, the nonlinear frequency dependency. This x corresponds to the is the initial value of the system of ODEs in the linear setting. Well, we cannot choose this component arbitrarily if we want to make a connection with the original problem. So we have to choose this x in a very special way. And I've written down here a very complicated formula, but what it says is that you make a linear combination of the two previous cases. So you basically make you decompose the starting values following a Fourier transform so that you can write this as a superposition of vectors of this form. And then you make the linear combination, and then you find that the Laplace transform of the solution is the solution of an algebraic equation. All right, let's apply that for this clamped beam problem. So here is the algebraic equation. I've used the Crank-Nicolson method on some time interval. This nonlinear function that we have here is relatively nice. So we have here a log plot, both the horizontal and the vertical axis. So the horizontal and the vertical axis in the log plot, and it looks quite nice. But of course, it's all exponentials. Now, this function can relatively easily be approximated by a rational function, and what I've shown here is a table that shows different things. So we're going to approximate this function on the imaginary axis for frequencies lying between 1 Hertz and Fmax. And we have for different values of Fmax the results about the stability of the equation. So the stability, how did we obtain that? By doing the actual integration and seeing if the system was stable. And we see that for a wide range of values of Fmax, the system was stable. Also, for a wide range of number of sample points on the imaginary axis, the system was stable. So in general, we had stability, which is quite nice. We noticed that if we didn't use the linearization, which leads to a DAE, so if you use the linearization which leads to a DAZ, then we sometimes did have instability. So removing the infinite eigenvalue was really crucial in this case to get these nice results. Next, I'm going to show a purely harmonic solution for 100 Hertz with 1000 sample points. I'm comparing between several values of the maximal frequency for the AAA approximation. And I used Crank-Nicolson and a very low tolerance for AAA to start with. And the results are here. So when we use a small interval on the imaginary axis, the results are clearly not very accurate. What you see here in blue is the modulus or the absolute value. Yeah, the modulus of the solution is actually the absolute value because everything is in real arithmetic. And in red, you have the error, the true error. And you see that only for 1000, when we choose an Fmax equal to 1000, we get a rather accurate solution. So the choice of Fmax is quite important. We have to choose the Fmax relatively large. Here we have another situation. We start with a constant initial vector, so initial value which is 0 for all negative values of time, and that means that for the linearization, we have to choose initial values of these forms, where phi are the rational functions, the barocentric functions in the rational approximation. And also here we choose different values of Fmax, and we see that also here Fmax has to be chosen relatively high to find a solution which is accurate. So we see that for the larger values of Fmax, we have solutions which are very close to each other. Similarly, when we use a harmonic solution from the past, so I use this function here for negative values of time, which leads to an initial value, starting value at time 0 of this form, we have a similar solution. So a similar situation, we have to choose a relatively large value of Fmax to have accurate solutions. Okay. What we have here is a comparison for different values of the tolerance for the AAA approximation. So what we used here was a relative tolerance for the approximation of the function. For this example, the nonlinear term is the dominant term in the matrix. So it really makes sense in this example to look at the accuracy of the approximation of the nonlinear function. What this actually means here, if you would solve the problem in the frequency domain, that would correspond to the a backward error of the linear system. Well, almost a backward error of the linear system in the frequency domain. And you see with an error 10 to the minus 1, we have a solution that looks good, but we have some error here. And for 10 to the minus 4, the error is acceptably low. And we see that we only need 12 poles in the rational approximation for this problem. So I'm already at the conclusions now for this talk. What I have done is use linearizations based on the AAA method for time integration of nonlinear frequency dependencies in finite element models. One of the conclusions is that we have to use a good linearization, so linearization that removes the eigenvalue at infinity. We are lucky that the eigenvalues at the poles all lie in the left half plane, and the reason is probably that the nonlinear functions are the result of damping terms, and the engineers told me that they can actually prove that these terms are indeed damping terms. But we have to choose enough sample points and a frequency range that is large enough for accuracy and sometimes for stability as well. The only downside of the method is that if we have many nonlinear terms in the matrix, so large M, that the complexity for computing the rational approximation can be quite high. That was also one of the topics that was discussed by Françoise Tisseur in her talk. And at the moment, we are working on the boundary element method, where we have n squared different functions, and where the difficulty to find a solution in an acceptable time is quite challenging. And at the moment, we're getting good results with that too. This was my talk. Thank you very much for your attention, and I'm looking forward to your questions.
Oh, thanks very much, Karl. This was a very clear talk, and we got a number of interesting questions. So I'm gonna ask, let's see if this works. We'll go to unmute. Yeah.
Yeah, thanks, Karl. Thanks for the nice topic and the nice talk. So I have two questions. Question one, the experience is that when you have a large number of sample points, that the conditioning of the rational approximation in AAA tends to go haywire.
Yep, correct.
Even if you get rid of the infinite eigenvalue. So do you observe that here too?
That's true. So what I use, I should have mentioned that. In my experience, when you use equidistant points, or when you use points in a logarithmic or exponential spacing, everything seems to work fine. So we use 100,000 points without a problem on the imaginary axis. So that makes 200,000 because you also have the complex conjugates.
Okay, yeah. So that's good news. Yeah.
But indeed, if you take them randomly, which some people do, you get quickly in trouble.
Yeah, and the second question that I had, I mean, these problems, I'm sure you can express them as dissipative Hamiltonian systems, and then you could take the full advantage of the techniques there. Do you know anything about that?
No, actually, I should look at that. That's a good suggestion. I'm making a note. Yeah.
Okay, the next question I think is by William. There we go.
Hi, thank you for the talk. I guess you addressed this a little on your conclusion slide, but I was wondering what you were doing to guarantee the stability of the poles in your approximations. Like in the fast AAA paper that you cited, they talked about computing the poles afterwards and then just throwing away the unstable ones. Are you just computing the poles and then testing if it's stable afterwards?
For this problem, we never had unstable poles.
Okay, so they never showed up when you were building the approximations.
So you may have found that if you do not take enough sample points, or when the frequency, not enough sample points basically, that you may have unstable points. So you have to approximate this function very well. Now the engineers told me that this function, they can prove it is a stable, I mean, it leads to stability, so the poles must be in the left half plane. If they are not in the left half plane, you probably do not have a good rational approximation.
Awesome, thank you.
Yeah, but I'm not, well, it's a very good question, in fact. And yeah, it's definitely something that we should look into. Yeah.
Hey, Nick.
Hello, Karl, that was great. Thank you very much.
Hi, Nick.
I made a comment in the chat
I
again
noticed,
related
yeah.
to stable points. I'd like to echo what Karl has said. In my experience with all kinds of problems, when I think something's going wrong with my rational approximation, it's usually actually with my sample points. And when I take more sample points or in the right range, usually that makes the difference. But again, and connected with William's question, as some of you heard me speak about at some point, Stefano Costa and I have a variation on AAA called AAA least squares, which just seems amazingly effective. And the idea is you do AAA in your barocentric basis, but then you actually throw away any bad poles and convert to partial fractions. You found the good poles with AAA, and then you just switch over to partial fractions. And that sort of seems to be a fairly universal technology for getting rid of poles in bad places. And as Karl says, for well set up problems, usually the poles in bad places aren't helping you anyway, so that typically little is lost when you do this. Karl, I don't know if you've tried that AAA least squares approach.
No, I didn't actually, no.
But it doesn't sound as if you've needed it.
Actually, it's, yeah, but it was on my list too, but we didn't need it indeed, yeah.
We all have long lists.
Exactly, and the lists get always longer, never shorter. That's a problem. But indeed, nice comment. It's true. It's yeah. There are still many things about AAA that about the practical AAA that still needs to be done, I think. Like selecting the sample points and so on. Yeah. Hi,
Okay.
Bernd.
Bernd had a question as well. Yeah.
Yeah. Hello. Thank you very much for the very nice talk. I found it very exciting. There is one point which follows a little bit the other questions. In the ideal physical case, you don't want to approximate your nonlinearity on an interval, but on the whole imaginary axis, no?
That's true, yes. Yes, that's correct.
So taking the sample points from a certain interval and more or less adapted to the interval, in fact, should cause troubles, no? Am I right? You want to have a good approximation on the half plane, in fact, no?
Yes, that's true. But of course, well, you can take the interval large enough so that you can enclose all the eigenvalues. Well, that you cover all the eigenvalues. But there is another reason. The physical problem is only valid for some frequency range. So the high frequencies, of course, you need to take into account the high frequencies for the stability. Not for the approximation, but for stability, and ensure indeed that you have all the eigenvalues with you. But for the high frequencies, they really don't play a role in the physics, because well, that's not a problem for us. Of course, it's a problem for the people who do discretizations of PDEs. Okay. But indeed, it's also an issue for the time integration, because if you cannot model properly the high frequency components, what are you doing? But that's indeed not our worry. We start from discrete systems. Of course, you could generalize that to infinite dimensional systems as well, operators in space, which is perfectly fine. But yeah, you're correct. Indeed, you have to take into account the full imaginary axis. But if you're high enough, so that you can do a kind of contour integral along around the eigenvalues, or an approximate contour integral, I think you're fine.
Okay, yeah, thank you very much. May I ask another question?
Of course,
sure.
Yeah.
There is a conceptual thing which I didn't understand fully. Why are you separating, approximating by a rational function separately all the GJs? Can't you just approximate the sum immediately and get a lower complexity?
That's a good question. François Tissot gave a talk about that. Indeed, you can do that. So in some way we do that already. So the poles and the weights are common for all the functions. So the only difference lies in the coefficient.
So you make the union of each rational approximation, the poles of each rational approximation. Is it
so where is it? I think it's here. So the poles and the weights are in here, in the E and the F. So they are the same for all. The only difference lies in the coefficient. So that's the only difference. So you use the same poles and weights for all the functions. And there are several techniques for determining such poles and weights.
Yeah. So it's a kind of simultaneous with a common denominator, a kind of simultaneous approximation.
Exactly. Yeah.
But there is not so much mathematics on that.
No, it's a lot of heuristics, because you can do a linear combination of the elements of A, for example, but that doesn't always work. You get the dominant term, but not the less dominant terms, for example. So, well, of course, it's problem dependent, but yeah, we notice that for eigenvalue computations, it doesn't always give good results. Maybe in this context, it might be good enough. I haven't tried it. Yeah, but these are all heuristics. There's I don't think there is a lot of theory to tell about that. Well, about convergence, of course, there is, but
no, it's just that I'm saying it's difficult.
Yeah, no,
I'm
it's not easy. Yeah.
Thank you very much.
It's one of the exciting things about rational approximation.
Any other questions? Fran, can I unmute you? Let's see if I find you in the list.
I see that Francois Tisseur has a question.
Yes.
For large M, why not using surrogate AAA with Leger-Bagby refinement for rational approximation? Yeah, you could do that. I don't see a reason why you couldn't do that. Yeah, of course. Yes. Yeah.
Maybe I can also ask a question. Karl, do you find it important to actually take care of the linear or quadratic terms separately? Because if you sample the nonlinear functions anyway, they should kind of be included in the rational approximants, shouldn't they? If you just choose the degree large enough.
Yes, that's true. So here I separated both. Yeah, I have no real answer to that. Well, of course, in this example, we know that the nonlinear term, so the problem here, yeah, this problem here, so this is really the term we want to approximate. And of course, you could take that term as well in the approximation, but this is definitely not a damping term. No. So you might get unstable poles when you do that. And of course, we don't want to have unstable poles.
And the other thing is that the middle term is usually generated from data.
Exactly.
And so and it describes friction and terms which are really heuristically interpolated. So the linear term is good because that's a finite element model. And the middle term is just a lot of heuristics.
Yes, and in fact, this is something that I could also have said about a few words. There is a lot of uncertainty about this one. So the K and the M, that's finite elements. It's very well understood. It's in theory and so on. You can discretize, that's very fine. But the damping term is usually the term in a model that is the less sure. So yes.
Okay. I think that's it. I don't see any other questions. So thank you again, Karl, for a very nice talk.
Thank you.